Hi everyone, this is Tyagarajan, retired Deputy Chief Engineer from Indian Railways. In this video, I am going to discuss something about the short welded rails and long welded rails and continuously welded rails. I think this video will be useful for the civil engineers in Indian Railways, the engineers who are preparing for any competitive examination in Indian Railways for further promotion. Also the students, civil engineering students who are very much interested to know about the railways. With this we'll go into the subject SWR, LWR and CWR. Okay, what is SWR, LWR and CWR? First let's see SWR and LWR. We want to say literally when the rails are welded for a shorter length, it's called a short welded rail. When they are welded for a longer length, it's called a long welded rail. This is something about literal explanation of SWR and LWR. So coming to the evolution of the welded panel, you see those days we were getting rails only in a standard length of 11 meter, 12 meter only for transportation and loading and unloading convenience. Though the steel plants were able to roll rails for a longer length, they made a standard length of 11 meter, 12 meter only for these reasons. And after the manufacturing of rails, the rails were transported to the site and track was formed using the rail length of 11 meter, 12 meter, used to say free rail. So we are making only free rail track. That means every joints, we were having a fish plated joints. The joints are connected with the help of fish plates and bolts. In course of time, we had been experiencing lot of problem with the fish plated joint. So that means comfort point of view we had some problem. So every joint they were facing some knocking, and maintenance problem we had more wear and tear the rails at joints as well as fishing components. And thirdly, the packing and sleeper also will get disturbed often, and frequent attention we have to provide. So because of these problems, there was a compulsion to eliminate fish plated joints, and eventually the welding of rail joints had been invented. Then we started welding of rail joints. First, to start with, we have converted 3 rails into 1 rail. That means every third joint we were having fish plated joints. Out of that, we are able to eliminate 60% of the fish plated joints. Then after that, it was contemplated, why can't we weld the third joint also? Why can't we weld the entire joints from one end to the other end? So because of that, the study has been conducted, what would be the repercussion if the entire joints are welded, and out of that, the track structures has been redesigned, providing some special sleepers and with the elastic fastenings, and providing some special expansion joints at the ends of the welded panel to accommodate the expansion contraction of the welded panel. So this is something about the evolution of the welded panels. And also because of the welding of rail joints, we had been getting a lot of advantages in comfort point of view, maintenance point of view, and safety point of view also. Because safety point of view also is very important, because fish plates, it's also prone for the failures. So often we have been facing a fish plate fracture and fish bolt snapping. So because of these advantages, and nowadays, it has been made compulsory to lay LWR, CWR everywhere. In order to that, we are able to get saving of fuel also by locomotives because of the provision of the smooth bed. Okay. To explain, see, this is your free rail track. Normally 13 meter rail length. Nowadays we are getting 30 meter rail line. So every 13 meter there will be joints. So the fish plated joints, always there will be a problem of maintenance, and when this track, when the trains are passing, definitely there won't be any smooth passage will not be the smooth. Riding comfort we can't expect. Every joint there will be some knocking sound will be there. Okay. Of course, the maintenance problem also will be there more. So because we are converted to 3 rail panel, converting 3 rails into 1 panel from 39 meter. So every third joint will have the fish plated joints. This way we are eliminating. And subsequently we started welding the entire length. Completely we are welding See, if it is more than 250 meter, normally we used to say it is LWR. Suppose we have stations A and B. So you want to weld the joints in between station A and B. So normally, we used to weld from this top point of the A station to the top point of the B station. Provided if we don't have any obligatory points, we can weld all the rail joints. So regarding obligatory points, we will discuss later in the coming slides. Okay. So this is actually LWR. If you are welding between the two stations, it's called LWR. But we cannot carry through our LWR over the points of crossing. That is why we are terminating our LWR at the approach of the points of crossing. We want to take through our LWR over the points of crossing through station, that's called CWR. So for carrying through our CWR, we have some instruction we are supposed to follow for strengthening the points of crossing. So that also we will discuss later in the coming slides. Okay, further I want to say something about the effects of the temperature variation. Because our railway track is exposed to the atmosphere, the hot sun. Okay. See, any material will undergo expansion contraction due to temperature variation. There will be thermal expansion or thermal contraction. Similarly, for our rail also, because of the temperature increase, the atmosphere, there will be expansion contraction of the rail. So, for accommodating the expansion contraction of the rail, so we are providing the gaps at each joints. Normally, the initial gap would be 6 mm while laying, and actually the fish plates joints are designed for maximum 12 mm. So that will take care of the expansion contraction normally. Because the scientific phenomena, the expansion, that is our change in length, equal to L alpha T. So delta is equal to change in length, L is equal to original length, alpha is equal to coefficient in expansion of the material. The steel material means it's having some constant. Some 1.15 to 10 to the power of 5 will be the constant. Okay, this is coefficient. T is equal to temperature variation, that is initial laying and subsequent increase of temperature. The difference will be the T variation, T temperature variation. So based on the this formula, phenomena, this expansion or the change in length will be equal to L alpha T. That means this will be, the expansion will be or contraction will be directly proportional to the length of the rod or rail and directly proportional to the temperature variation. So more the length, more will be the expansion contraction. More the temperature variation, more will be the expansion contraction. Here, this is 13 meter rail is there. Let us assume 13 meter rail, and for that the gap has been designed. But at the same time, when we are converting into SWR, we are converting 3 rail to 1 panel, and the length is increased. Now the length becomes 13 meters. Once the length is increased, automatically the expansion contraction will be more, okay, at the joints. But whereas we are providing the same fish plates here, same fish plated joints here, same design only we are providing. So as well as the SWR is concerned, it is now it becomes little critical because of increase of the length. But here it is comfortable because sufficient gaps are there. But here the gaps are very tight. So it is our the engineers who are maintaining the track has to take care properly the SWR. They should ensure always the proper gaps are available or not. Okay. So sometime what will happen because of the creep, because movement of the rails, loose fastening, there will be the jammed joints. There will be the gapless joints. So some 3-4 rails will be continuously, there won't be any gap. In that case, what will happen? When there is expansion, temperature increase is there, you will try to expand, whereas there is no gap. Because of that, there will be a substitute. There will be a setting up of internal force. Normally, when the expansion is restricted, there will be development of compressive force. So suppose compressive force you see, and for taking care of we have the ballast and all, because sometime there will be ballast deficiency. If the more ballast deficiency, sometime what will happen? You will avoid it opportunity, try to buckle. So As far as SWR is concerned, it is comparatively it's critical than our free rail track. That is why you should take more care of this SWR. Similarly, in the case of LWR, CWR, we are continuously welding the joints from one end to the other end. Just imagine, because continuously what will happen? So as we discussed here, the expansion contraction will be directly proportional to the L and the T. So there will be more expansion and contraction. And when the movement is restricted, there will be setting up of internal force. So, this one. But however, we are providing joints at the both ends. This is specially designed, not like fish plate joints. It is a specially designed joint that's called switch expansion joint we are providing. That will accommodate more care. At the same time, the functioning will be a little different than your this SWR. So to further explain, to define technically and what is SWR and LWR, we will see now. So earlier we had been discussing something about the different type of panel, welded panel and free rail track and SWR and LWR. In what way it differs and what way the temperature affects. But if you want to technically define the SWR, earlier I told simply when it is welded for shorter length, it is called a short welded rail. That is literal meaning, literal explanation. But technically, how it is defined? If you want to define technically, a welded panel that contracts, expands throughout the length due to temperature variation. The expansion contraction will be throughout the length of the rail panel. Suppose this is 39 meter rail, but the expansion contraction will be throughout the length. Suppose center means this side will expand this way and this side will expand this way. So there will be some expansion, contraction that will take place throughout the length. So 50% expansion will take place this side, 50% this side. So this is your technical definition. So coming to the LWR, how is it technically defined? It is not like a SWR. Here the expansion contraction will be some portion of the welded panel. Only at the ends of the welded panel will have the expansion contraction. That will be the breath-in length, where the breathing takes place. The central portion will not undergo any expansion contraction due to temperature variation. That's called fixed length or non-breath-in length. This is a technical definition. When the welded panel is more than 250 meter in broad gauge, will normally function as LWR. This is a definition, technical definition given in the Indian Environment Manual. This is something about. So this is your central portion where we won't have any expansion contraction. Only in the breath-in length there will be expansion this way and this way will take place. The portion where the expansion contraction takes place is called LB. That's called breathing length. This is about that. Now we will go to the LWR in detail. How the LWR is functioning due to temperature variation. What is the concept? What is the concept? In what way the temperature affects the functioning of the LWR, and what is the phenomena that? Let us go in detail. As already discussed, you see the delta L is equal to L alpha T. That is a change in length. Normally used to change in length. It's called expansion contraction will be L alpha T. The delta change in length of the due to temperature variation, and L is the original length, and alpha is the coefficient in the expansion of the material. We are using here rail steel. Rail steel we have constant, some 1.15 to 10 to the power of 5, and T is your temperature variation. That means initially when you are measuring what is the temperature, and after the some time when the temperature increase, the difference will be the temperature variation, and for the variation how much expansion contraction takes place, that will be equal to L alpha T. Here to say something about it, any rod, as I told you, any material will undergo expansion contraction due to temperature variation. Let us assume a rod we are placing on a floor. We have no friction at all. It is just no friction in the floor. What will happen when temperature, there is hot sun, temperature is increasing. When temperature is increasing, what will happen? There will be expansion. When temperature decreasing, there will be contraction. the amount of expansion contraction is equal to delta L. Suppose both the end means delta 1 plus delta 2 equal to delta L. This is L alpha T. So once the movement is freely permitted, the force will not be in the material. Suppose let us assume the rod does not have any force internally because of the expansion contraction is permitted freely. Okay. But when the movement is restricted, completely the movement is restricted, what will happen? So let us see here. Okay. Now let us assume this is the same rod. Here we are completely fixing the expansion or contraction will not be permitted in such a way it is fixed. Both ends are fixed and every point also we are fixing it. Okay. Now that there is an increase of temperature, assume there is an increase in temperature. The temperature is now increasing. Because of the increase in temperature, what will happen? That rod is trying to expand, but whereas the expansion is not permitted, is resisted by the fixers. You are fixing at all the ends. At the same time fixing every point. Okay. Also the rod. Once the movement is not permitted, restricted, there will be setting up of internal force. Because of the temperature variation, when the movement is restricted, there will be setting up of thermal force. The thermal force equal to AE alpha T. Okay. When the delta L is 0, movement is 0, there will be the maximum force. Okay, AE alpha T. So earlier what I have seen, we are permitting delta L, but whereas the P is 0. Previous case, the P is 0 since the movement is completely permitted, freely it was permitted. But once the movement is restricted, there will be setting up internal force due to temperature variation. In that case, it is called thermal force. So, how we got this is equal to AE alpha T. How we got this one? Because normally, already discussed, we have the basic, the principle, delta L is equal to L alpha T. And E equal to what? Strain. We used to say, already we would have studied in applied mechanics. Strain equal to change in length by original length. And if you are converting it, substituting this one L alpha T divided by L. But where Young's modulus should have studied, Young's modulus is equal to stress by strain. So stress equal to load by area. So everything are substituting. E equal to P by AE. The P equal to then P equal to Young's modulus into strain. Okay. Then P equal to A into strain into E, and whereas that P equal to A into E into alpha T. Okay. Because E equal to alpha T. So we are substituting here A into E and A into Young's modulus. And E is equal to alpha T. Okay, then alpha T. So P equal to AE alpha T. This is a thermal force equation. Here you can see the force is thermal force is directly proportional to the cross-sectional area of the rail. A is equal to cross-sectional area of the rail. Suppose we assume rod. Let us assume this is a rod. It's a cross-sectional area of the rod. E is equal to Young's modulus of the material. Suppose if it is steel, if it is rail steel or steel, we have the Young's modulus value. If it is normally rail steel, we used to have 2.15 10 to the power of 6 kg per centimeter square. And alpha is equal to, already told for the steel, 1.152 into 10 to the power of minus 5 per degree centigrade. And T is equal to temperature variation. That is the difference between the initial temperature and the final temperature at the time of measurement. So this will be the equation. So this is the equation. So here we can understand here, more the cross-sectional area, more will be the force, and more the temperature variation, and more will be the force, because they are directly proportional. Only the two variables are there. That's what the P is concerned. It based on your cross-sectional area and T, because the E alpha is constant. Okay, for the particular material. If you take the steel, the E and alpha is constant. Okay, this is something about the equation for the thermal force. But here In our case, what will happen? This is not simply, we are not placing on a floor, we are not placing on the floor, and we are not completely fixing, but anyway we are fixing it. We are placing the rail on the sleeper, and rails are fastened, fixed with the help of elastic fastenings, some clips and all, firmly we are fitting, and the entire track frame is embedded on the ballast, and completely we are packing, consolidating. But however, it is not like a concrete. Not a concrete. Concrete means completely fixed, but it is not a concrete. It is only the ballast. The ballast is just like a elastic medium, and we can't say it is completely for complete fixity, 100% fixity. We can't say it is because of the elastic medium. It is partially it is fixed. Partially it is fixed. Okay, it is fixed. So in this case, in this case, what will be the effect of temperature? How the welded panel is behaving? Okay. So here you see, this is our welded track. So completely we have laid on the ballast, completely packed and consolidated. It is okay in this condition, and there is a temperature. There is an increase of temperature. Let us assume what will happen here. In this case, because of the increased temperature, the rail will try to, the entire track frame is trying to expand this way, and let us assume it is an increasing trend, trying to expand. But whereas the expansion, it will be resisted by the ballast resistance, because ballast some offer resistance that will go through the sleeper and to the rail, because it is firmly fixed. For each and every sleeper, you will offer some resistance and trying to restrict the movement, trying to restrict the expansion due to temperature variation. Let us assume that the ballast resistance is 1000 kg per meter. It is approximately, normally ballast resistance will be 1000 kg per meter per rail. We have two rail, per rail it is 1000 kg per meter. So similarly, both ends. This is a complete welded panel. This is this side. This is the end of the welded panel. This is the other end of the welded panel. As already discussed, only both ends only have the breathing length. So let us how we say it is only the end only is the having the breathing. So because of the offering of resistance, ballast resistance, it goes through the sleeper to the rail, trying to restrict the movement. So when it is giving 1000 kg per meter, suppose per sleeper, let us assume some 600 kg. Like that, this is 600 kg. Okay, one sleeper. Again on the then two sleepers, it will have 2 into 600 kg. So 3 into 600 and 4 into 600. Like that, if a ballast offers some resistance to the rail, and controlling the movement. So because of the ballast resistance, gradually the resistance is building up. It's okay. Every sleeper, is offers some resistance, and one particular point, you see, there will be a maximum resistance will be built, and that will control the entire movement. So if you see here, when the maximum force is there, the movement will be 0 here. So complete movement is here stopped. The movement will be 0, but whereas the maximum force will be there because of the force, whatever movement is completely, I discussed, when the movement is restricted, they will be building up a force. They will be setting up a force. Here, gradually the force is building up, and one particular point, the entire movement is restricted. There, the maximum force will be there. The same time here there is no building. At the point end, there will be a maximum expansion. That force will be 0. So once force is 0, the movement will be maximum. Once the force is maximum, the movement will be 0. Similarly, both things. So this portion where we have the movement, the expansion, is called breathing length. Okay, this portion between the two breathing length will have will not have any movement, will not undergo any expansion contact due to temperature variation. It's called the fixed length, or called non-breathing length. So okay, This breath length will be, as I already told you, this is based on your cross section and the cross section area of the, because here it is a rail steel, no, rail steel, already we know the E is equal to 2.15 10 to the power of 6 kg per centimeter squared, alpha is equal to 1.15 to 10 to the power of minus 5. This is constant. The A and the T will be the variable. So more the cross section, more will be the force, and more the temperature variation, more will be the force. That is why compared to 50 gauge, 60 gauge rails, more force will be there, because the area of cross section will be more. At the same time, it is that is why we need piece sleepers and ballast, and piece sleeper nowadays we are using pre-stressed concrete sleepers and completely well packed and consolidated and ballast we are ensuring here, ballast but we are ensuring, so that there will be good offering of resistance to control the moment, because once the moment the length of breathing is more, there will be more expansion. So we try to control the movement as maximum as possible. So this is about the function of the LWR. But whatever the length, whether it is a 1 kilometer or 2 kilometer, 3 kilometer, 5 kilometer, this will be the constant. The breathing length will be constant. It is based on this cross section and temperature variation, irrespective of the length. Okay, even 20 kilometers. Suppose let us assume we have the 100 meter breathing length. The 100 meter breathing, even if it is 1 kilometer is 100 meter to 200 meter, the non-breathing length will be 800 meter. Even a 20 kilometer you have, so 100 meter you have, so 9.8 kilometer will be the non-breathing length. Okay, this is something about it. Okay, and the breathing length, as already I have told you. So the breathing length equal to breathing length into R. This is force, the LB into R. LB means breathing length into R. How much distance? So per meter it is called per meter. Per meter it is 1000, means for total length, okay, how much force will be there? So LB R equal to P. So breathing length equal to P by R, and LB breathing length equal to AE alpha T, P by R, AE alpha T divided by R. This will be the equation. If you want to find out the breathing length, this will be the equation. Okay, it differs based on the cross-sectional area and the temperature variation. Okay, so this thing we will discuss in detail in the next topic. We'll discuss. Okay. Okay. And also, as far as this ballast vessel is concerned, based on the study, this consolidated track, for consolidated track, it is 1470 kg per meter per rail. If it is through packed, it is 1220, because there is a disturbance due to the through packed, this packing. And if it is de-skinned, further this ballast is getting disturbed, and because of that there will be some reduction. This will be 1040. So this is your for various conditions, this will be the ballast itself. But for any calculations and all, we used to have approximately 1000 kg per meter per rate we are considering for calculation of approximately, so finding out the breathing length. Okay, some of the definitions also you should supposed to know in case of LWR. We will first discuss about the LWR, and later the next topic or next video will discuss about the SWR. So the breathing length is the length at each end of the LWR CWR, which is subject to expansion, contraction on account of. So breathing length means that is, as already discussed, the ends where the expansion, contraction will be the breathing length. Switch expansion joint is a device. I already told you, special device we are providing at the ends of the LWR for accommodating the expansion, contraction of the LWR. This is called a switch expansion joint. It is specially designed. It is just like a splice arrangement. Nowadays the initial gap it is 40 and maximum design for 80 mm. Nowadays it is there. Okay, even some case also is there, 60 mm initial gap, and even can be designed about 120 mm also is there, and we have even 190 mm designed gap also is there for a special some situation. Okay, so whatever may be, this is the switch expansion joint. It is provided at the ends of the LWR for permitting the expansion of the contraction of the adjoining breathing lengths due to temperature variation. So rail temperature is not ambient temperature. Rail temperature is rail temperature. Now whatever the temperature rail is having physically, it's a rail temperature. We used to measure using the approved type of rail thermometer we have. Okay, this is about the rail temperature. Mean rail temperature is normally each and every location there will be mean rail temperature is the average of the maximum minimum rail temperature. Suppose in a particular place, if you take based on your record, you can say what is the maximum temperature and minimum temperature. Okay, taking the average, this will be the T mean. Okay, T mean. This is very important. Temperature. This with reference to this only we are fixing all limits, temperature limits. Okay, we are fixing it. We will discuss in the coming topic. We'll discuss about it. Okay. So coming to the recording of temperature, we have approved type of thermometers. The Indian Railways we have the approved type of thermometers. We have three types, namely embedded type, dial type, and continuous recording type. The three types of thermometer we have. Embedded type is, of course, this is our picture. This is ordinary thermometer. It's fitted in a rail piece. The top of the head cavity is formed, and the bulb is inserted and filled with mercury and sealed. Okay. Since it is having the close contact, this reading will be reliable. It's giving almost some accurate reading. It will keep. So it takes 25 to 30 minutes for giving the exact temperature of the rail. Okay. This is something about it. Then the other one is dial type. It just is a bimetallic type thermometer. Actually, it's just like a watch. It looks like, and it's the back of that it's having magnets, so that we will be able to fit the thermometer in the web portion of the rail. Even the traffic condition we can record. So this is very simple one. It takes 8 minutes for recording temperature. This is something. Okay. Then this is actually the picture of this one. It's very simple. This one, dial type. Okay. And the third one is continuous recording type. But the whatever we have said earlier too, we can take you to the site. Okay, take you to the site and we can record, because but whereas this one, so this one cannot be mobilized. Okay, this is slightly it's bigger one. It is just fixed on the frame. Normally this entire arrangement will be set up in the section in your office. Okay, office, and okay, actually this is a arrangement. We have the big board will be there, and it is just like a clock. The winding mechanism is there. It will be like a rotating drum, and over that we are fixing the graduated chart. Okay, this center. Okay, center pivot, this one, and this arrangement. Actually, since sensing element will be there, it is just connected to the rail piece here. Rail piece fixed on the floor, and further it is connected to a tube. It is filled with the mercury and connected to the coil, and further connected to the pin. So once the temperature is there, increase or decrease, according to the thermal condition, the mercury will expand and it will operate the coil, and finally it will operate the pin also. And since it is rotating, and this recording will be continuous. So that you can take the complete temperature record of 24 hours or 7 days according to our setting. Okay, this is something about it. Okay, these three type of thermometers normally we have in the Indian Railways approved type. On any other type approved by RDSO, whatever, sometime it will be approved. Actually, the thermometer is very important, because as far as our LWR is concerned, temperature is playing important role. So each and every action, maintenance action, or maybe each and every action, it is all based on your temperature. For each and every activity, we have been fixed with some temperature limits. So temperature, the thermometer should be proper. So that is why we have to cross check with other thermometers whether it is working or not. All thermometers working on whatever available with section engineers and other gangs who are working in the field. Okay, it should be cross checked. If anything found defective, it should be discarded. Okay, this is something about thermometers. Then coming to the T mean. So as I already told you, the T mean is very important temperature. With the T mean only we are fixing other various temperature limits. Okay, for carrying out the various activities in LWR. So how to ascertain the T mean of a particular section? Okay, on section engineers there is section. You must know is T mean. Okay, how to ascertain is T mean? So for that only we need temperature records. If that section engineer is having the 5 years record, past 5 years record, based on that you can ascertain. So taking the average of T maximum, T minimum, will be able to get the T mean. Okay, so that's. Sometime that records may not be available. So in that case, what is to be done? If no records available, so for that one, temperature map available. It's given on the Indian Railway Permit Manual, and in that or various places that temperature details will be available. So that can be referred, and that you can keep as is T mean. Okay, actually this is the temperature map. As far as India is concerned, it's divided into four temperature zones. Zone 1, 2, 3, 4. Okay, so the various places they are given where over the India they are given the temperature details. Suppose Madras is 57. Madras we will see here. Madras somewhere here. Madras 5739. Okay, 5739. So whatever the values within the bracket, that is mean temperature. That's T mean temperature. The outside the bracket is range. The range means that is the difference between the T maximum and T minimum. Okay, that is range. So like this, each and every place they given, and we cannot get exactly the particular. Suppose the section is Vidupuram. The Vidupuram you cannot get directly the place, and he has to refer the place where it is available nearby. Okay, that will be that you can take it as a T mean and other range of temperatures. Okay, if you look at this map, see here there are 4 zones. I told you, it's divided into 4 zones. So zone 1, the range of temperature is 40 to 50, and zone 2 51 to 60, zone 3 61 to 70, and zone 4 you see here 71 to 76. So there is a maximum variation in zone 4. So but whereas in the zone 1 it is 40 to 50 only. So the zone 4 is very critical, because where we get the maximum variation. Okay, of course zone 1 is little comfortable. So these are all 2, 3 and all moderate. That means here you see zone 1 is Kerala coastal area, then zone 2 is Tamil Nadu, Andhra, this and all, southern part, and zone 3 is a central part of India. Okay, zone 4 is northern side, Delhi and all. Okay, this area. So this area is very critical. This of course is variation is less. Why I am telling already, as I discussed, the temperature is playing important role, and the force, force equation we have seen formula, that is force equal to AE alpha T. That more the temperature variation, more will be the force. Okay, at the same time, even the breathing also will be more, and more expansion contraction will be there. Okay, so that is why the variation wherever this is more, that portion will be critical. Here zone 4 is variation is more, 71 to 76. Since there is more variation, this portion is very critical. So all activities, maintenance activities and all, we must be very careful. Okay, following the temperature limits. Okay, this one, and of course in zone 1 it is only 40 to 60. Okay, this is something about it. Okay, this temperature room actually based on the study by RDSO, they have made this map giving the T mean and range of gaps in the various locations. That has been consulted with this meteorology department with the temperature. They have the ambient temperature, no air temperature. We have rail temperature. We have taken the various places. Some 22 places they have taken. Some times back, stations they have set, and they have taken 2 years they have taken the temperature records and correlating with the temperature records of the meteorology department, and they were able to get temperature to various places. So that has been listed now and mapped now. Okay, map here. So this is about the temperature map. In the absence of our temperature records, we can follow directly the temperature details available in the map of your section. Okay. So now coming to our desussing, the definition is desussing temperature. Desussing is the operation undertaken with or without rail tensor to secure stress-free condition LWR at the desired or specified date. This is something about desussing process. That means this is the process, because as we have discussed earlier, normally the LWR is laid. Laid means the completely rails are welded. It's fixed in the sleepers and firmly. Okay. This while fixing, that fixing temperature is called normally installation temperature. So the installation temperature normally uniformly, on temperature we are fixing the rail with the sleepers fastened down. Okay. After that, what will happen? This is started functioning. When temperature goes up, there will be compressive force. Increase of temperature, and goes down, there will be down. There will be formation of tensile force. That is normally we are supposed to fix our installation, fixing our rail with sleepers. That means installation temperature almost close to the T mean. That means average of maximum minimum. T mean almost close to the T mean. So that when temperature goes upper side and goes down, compressive force and this one tensile force almost we are managing equally. Okay. So this is the way we are doing it. But what will happen after some time, course of time, because of disturbance to the track, normally there will be loose fastening will be there, renewal of fastening will carry out, and sleepers will carry out. There will be ballast efficiency, there will be fracture, and used to replace the fracture portion, substituting with the cut rail and all. So many disturbance when you are doing it, the installation temperature got disturbed. Ultimately, what will happen? See, this is a rail installed. When temperature goes up, this will be your force diagram. When temperature comes down, this will be the force, tensile force comes this diagram. But in course of time, what will happen? Since the installation temperature is completely disturbed, there will not be the uniform force will be there in the rail. So here you see, it's just going beyond the limit. So this area will be critical. And suppose when we have any balance efficiency, and because of the force developed is exceeding the limit, there is chance for the buckling. That is why we are supposed to ensure always the rails installation installed at the mean temperature always should be maintained. But actually the temperature at which we are installing is called normally desussing temperature. Okay, at which we are ensuring the rail in a stress-free condition. Okay, this is something about it. And how we are getting whether it is functioning erratic or not. Suppose for the sake only we are having the SEG. SEG is an indicator. And SEG is an indicator where the expansion contraction takes place. Okay, and there will be gaps. Normally we used to measure the gaps. Manual provides gaps. How much gap should be available for the various temperature, rail temperature. So the range of gaps will be available, and we have to compare with that whether the gaps are within the range, within the limit or not. We have to check up whether it is outside the range, means the LWR is not functioning properly. So erratic functioning is there. Then we have to go for desussing temperature. Again we have to what to do? We have to release all fastening and all, and duly creating the gaps at the both ends. This approach of the SEG, releasing all the lockout of stresses. We will install at one temperature. That temperature is called desussing temperature, prescribed limit. They have given the prescribed range of temperatures. The next slide I will show what is the prescribed range of temperature for carrying out destressing operation, at which destressing has to be carried out and entire locked force has to be released and the fasten. This is something about in that regarding destressing in detail we will see in the next slides, coming slides. Okay. This is about the destressing process, and the temperature at which you are carrying out this operation is called destressing temperature. That is normally the average of rail temperature during the period of fastening. There is the beginning and the end. We are taking the average. That will be this temperature of the particular LWR. Okay. So normally each and every LWR will have the destressing temperature. Normally at what temperature we have done destressing. Okay, that should be noted down. That should be available. The record should be available. So based on that only, all other further operation will be carried out. Okay. Okay. Anyway, next coming slides we'll see in detail. Okay. This is something about it. As I told you, these are the limits. So if you want to carry out the destressing operation, destressing operation, this range of temperature you must follow. For zone 1, 2, 3, I told you zone 1, 2, 3, southern side and southern side and central part, except the northern side. Okay, the zone 1, 2, 3 for all rail section we must carry out the destressing at Tm to Tm plus 5. Okay, Tm to Tm plus 5. This range only we must do destressing operation. So where we have more variation, critical area, there see Tm plus 5 to Tm plus 10, the case of 2 kg, and other rails, other rail Tm to Tm plus 5. So already I discussed, normally we have to fix now close to the Tm, but here you see zone 1 and 2 Tm plus 5, Tm to Tm plus 5, and whereas in zone 4 Tm plus 5 to Tm plus 10, somewhat higher side they fixed the destressing range of temperature. Why it is fixed like that? Let's see in the next slide. Okay, temperature is very, very important. See here, destressing, destressing is the process at which we are carrying out the releasing of all locked up forces, and the rail getting installed at a uniform temperature. Okay, that temperature normally we must have for various rail section zone, and they are given the range. We are supposed to follow that. Suppose here you see we are doing the installation of the LWR at T mean. Let us assume the total variation is 60 degrees centigrade, 60 degree. That means the T mean will be 30 degree, let us assume. And when we are doing a destressing at 30 degrees centigrade, when temperature goes up to the maximum, T maximum, what will be the variation now? 30, here 30. So 30 degree variation will be there. At the same time, when the temperature goes down to the extreme, that means to the T minimum, again the variation is 30. So the buckling force will be equal to, okay, for a variation of 30 degrees centigrade. Similarly for tensile force also, in this case 30 degrees centigrade. So force will be equal. But actually we are not doing like that. Slightly we are fixing at a higher level, higher side. Instead of doing the destressing instead of at Tm, we are doing the destressing at Tm plus 5 or Tm plus 10. Slightly we are keeping the higher side. Why means when this side goes up, there will be chance for the development of setting up of compressive force, which is responsible for buckling. But whereas when it's going down, falls down, it develops tensile force that is responsible for the rail fracture and well fracture. But here, see, the compressive force very, very critical, because it's causing buckling. Buckling is very, very dangerous because the alignment is getting distorted. Where tensile force, even though there is a rail fracture, the alignment will not be disturbed. Only the gap will be there. Meantime, safely trains are negotiating over the fractured portion. But I can't say it is not serious, but comparatively, the buckling is very, very critical, because once the track is buckled, alignment is completely distorted, definite derailment will take place. That is why we are very much bothered about the buckling. That is why we want to reduce the variation this side, so that buckling should never happen. So compromising the tensile force and rail fracture. So that is why suppose we are keeping our decelerating temperature at Tm plus Tm5, the variation will be only 25 instead of 30, 25. Of course here 35. So here tensile force will be for 35 degrees variation, here compressive force for 25 degree variation. Okay, like that. So suppose we are keeping in still higher side Tm plus 10, here only 20 will be there, here 40 will be there. So for 20 degree only compressive force will be there. That is why higher section, suppose 60 kg and all, normally used to keep, okay, and particularly zone 4 where we have the variation, where we have the more variation, normally they are going for Tm plus 10. That is why, because buckling should never happen. That is why we have the decent temperature is fixed slightly Tm plus 5 higher side. Heavier section zone 4 and all, you see Tm plus 5 to Tm plus 10. This is the reason why this distressing range temperature has been slightly different. Instead of T mean they are fixed in the higher side. Okay, is something about it. And also I told this one more thing. In the temperature map they are given 57 and 39. 39 T mean, that is only very important temperature. What is 57 T? That is means range. That means difference between the T maximum and T minimum. Then what is your T maximum minimum of this section, this area, this section? How to find out? Okay, here Tm is 39, range is 57. That means T mean is equal to 39 means so T maximum is equal to 57. Total is 57. 57 divided by 2. 39 plus 57 divided by 2, 67.5. And T minimum will be equal to 39 minus 57 divided by 2. 57 divided by 2. Here it is 10.5. So the range is 57 and the T mean is 39. T maximum will be 67.5 and T minimum will be 10.5. Like that you will be able to find out this one. Okay. So this is your rail fracture photo. You see, even though there is a fracture, somehow chain can go pass, okay, safely. But you see the buckling, it's completely distorted. So in this case, a train goes, definitely there will be accident. That is why you are very much concerned about the buckling than the rail fracture. And for that, we want to reduce the buckling force, so variation temperature in the higher side. Okay. And also the LWR on wider base sleeper with 60 kg rail may permitted with the reduced decelerating temperature. So already we have seen the temperature limit for carrying out the decelerating operation. Zone 1, 2, 3 and zone 4. Okay, the two limits, this thing we have seen. Tm to Tm plus 5 and heavier here zone 4 Tm plus 5 to Tm plus 10. But here in case of wider base sleeper when you use, so of late Indian Railway has introduced a wider base sleeper. We have the PS sleepers, we have standard sleepers. This is now in latest we are using wider base sleeper. It is base will be wider, heavier in nature. So that is why once we use this, once the base is wider, there will be contact area will be more and ballast resistance offering will be more. At the same time, being heavier also it will be more intact to offer more resistance. That is why it's comparatively heavier and they have slightly changed the range of temperature. Zone 1, 2, 3 Tm minus 5 to Tm, and whereas zone 4 Tm to Tm plus 5. Okay. So this is a range of decelerating temperature they have. That means they have gone minus side in case of zone 1, 2, 3. Because of heavier, it takes care of buckling more. That's time they want to take care of fracture here in this case. Of course, in zone 4, temperature is more, it's critical, that is why still they have in the higher side, Tm to Tm plus 5. Okay, this is the range. Only in the case of wider base sleeper, this is the range of temperature we must have for carrying out desourcing operation, TD. Okay, and now otherwise, whatever discussed earlier, we are supposed to follow. Here, breath length. So already we discussed, in the earlier in the concept functioning of the LWR. So when the expansion contraction is not permitted, there will be setting at an internal force. As far as LWR is concerned, okay, it is only the on elastic medium. Okay, placed on the elastic medium elastic bed. So only the ends, it offers some when you are trying to expand. The ends ballast is offered and gradually force is building up. In one particular place, the entire moment is restricted where the maximum force will be developed. Okay, that portion will be full of maximum force, and the ends will be no force, but whereas there will be movement will be there, maximum. So that we have seen. That portion where the breathing takes place is called breathing length. So breathing length, for various this thing. Because normally as per definition, when the length of the LWR more than 50 meters, it is defined as a LWR. That means assuming both sides 200, 100 breath length, in middle 50 meter, okay, that will be LWR. But it will be approximate. The breath length, whatever they it's approximate. But exactly how much the breath length will be there. So this is based on the force. We have already seen P is equal to A alpha T, and based on the ballast resistance. So according to the rail section and temperature various zone, and this has been eroded. How this has been eroded, we can see the example. Okay, here let us see breath length. It is approximately, they were telling some 100, some total to 250 even is there, 125, 120 also. It is only approximate, but actually how much will be the breath length for various cross sectional and zone, because as far as breath length is concerned, this is the formula, that is AE alpha T divided by R, that be P by R. P already we have discussed, AE alpha T, and R is ballast resistance. The breath length equal to AE alpha divided by R. That means it is directly proportional to the cross sectional area and the temperature variation, and inversely proportional to the ballast resistance. So more the ballast resistance, less the movement, breathing length, and vice versa. Like that, more the cross section and temperature variation, more will be the breathing and vice versa. Something about it. So let us assume we will take 60 gauge rail. So rail section is 76.86 centimeters square cross sectional area. And let us assume it is a temperature, zone is 2, zone 2. Zone 2, what is the maximum variation? We'll go zone 2, maximum variation 60, maximum variation 60. Maximum variation is 60, okay, 60. And maximum temperature variation in zone 2, variation how much? This is range, maximum range is 60. What is the maximum variation? Suppose assuming that we are zone 2, our range is how much? Desourcing range Tm to Tm plus 5. Let us assume we are doing desourcing at Tm plus 5, 35 degrees centigrade when we are doing it. What will happen? Maximum variation how much? Here this side 25, this side 35. So maximum variation we can take 35. Here 35. Assuming we are doing a desourcing at Tm plus 5. If that is the case, variation will be more in the tensile side. Temperature decreasing side. In that case, variation will be 35 degrees centigrade. That we can take it as that variation is 35 degrees centigrade. And E alpha and already we know they are all constant. And R here we are approximately taking 1000 kg only for this purpose. But already as we have seen, various studies they give 1200, 1400 something they given. But even then for this calculation purpose, for safer side, 1000 kg per meter per rail approximately is taken. So with this this one value, if you are substituting here, we will be able to get the value of 65.39 meter. Will be equal to 76 area, 2.11 10 to the power 6 is your this one E, and alpha is 1.1 10 to the power 5, and 35 degrees centigrade is the temperature variation maximum. Okay, and 1000 is your ballast resistance. With this we are getting 65.39, and this one 66 meter approximately you are getting, okay, you are getting. This is your this one. So here 66 for zone 2 sleeper density 1060 only, this one 66 meter we are getting. This is way we got this like that for various this one zone and rail section. This will be your this one breathing. In the case of wider sleeper, similarly ballast resistance is a little more. Okay, with that they are finding out the breath length for various rail section and zone. Okay, and sleeper density also. This is your sum of the definition of the some temperature, prevailing rail temperature. That is the temperature at which the whatever operations, any operation, maintenance operation, laying operation we are carrying out. At which that's called at what temperature we are doing it. Prevailing. That temperature is called temperature prevailing. It's connected to desussing. Okay, operations connected to desussing. Okay, and stress-free temperature is the rail temperature at which the rail is free of thermal force when tensors are replaced. So already discussed, we have been doing the desussing operation. We are doing in two way. One, desussing the normal way, manually we do it, and another this way is desussing with the rail tensor, some hydraulic, using hydraulic instrument. There only we are freeing the completely, removing the fastening and freeing all this one, locked up forces by tapping and all manually, and during one particular temperature prescribed, and we are fixing the rail back uniformly. Okay, that is. But here, we are using hydraulic tensor. That means artificially we are inducing a force in the rail. That means anyway, in detail we will see later in a separate video about this desussing operation with rail tensor. Anyway, roughly to say, suppose we have that we have been given no temperature limit for desussing operation. Suppose Tm plus 5 to Tm plus 10 or Tm to Tm plus 5 we should carry out. Normally we have the block, we are getting the block only in the night time. Daytime, of course, normally when we want to plan desussing, we have to see whether we are able to get the range of temperature or not. Then only we can carry out. So suppose daytime is some block we can't get, some traffic is full, traffic continuously is there, we are not able to get the block. Only we are able to do the desussing operation night, we are able to get the block, but that time we will not be able to get the range of temperature. How will you do it? So when you want to do any desussing operation lower temperature, okay, prescribed is suppose Tm plus, let us assume 30, T mean is some 40, then 45 degree we are supposed to do the desussing operation, but 45 degree will not get it during night time. So what you will do, we will do it at a lower temperature. Suppose assume it is 30 degrees centigrade. So difference is 15 degrees centigrade. So 15 degrees centigrade we are artificially inducing the rail, inducing the force in the rail, as if when the temperature goes to 40 degrees centigrade there will be stress-free condition. So that is the concept, with that way, and that way we are doing the desussing. In case of when you are getting the lower temperature, and particularly during night you want to carry out, you will do it with the rail tensor with hydraulic equipment. Okay, in detail about the desussing operation with rail tensor we will see later the next video, of course. Okay, this is something about this concept of the LWR functioning and all, and the temperature, how it's playing important role. Okay, so all these things were discussed. Okay, without conclude this video, and the next video will go into the and the next perimeter location for lake LWR, and subsequently maintenance. And also we will see something about the destressing operation. We do know, as already discussed, there are two type of destressing we do, one without right hand saw and with right hand saw. All those things you can see, and everything we'll see in the next video. Okay, coming videos. Thanks a lot. Thank you.